Okay, so the first step in a soil mechanics problem for slope stability is to actually understand what the problem is. So if we look at this slope in figure 1, we have a material that has a phi dash, so an angle coefficient of friction of 28 degrees, and a C dash, so that is therefore apparent cohesion of 5 kPa. The soil is saturated, so we know, and it has a unit weight of 19.2 kilonewtons per meter cubed. So using the method of Fellenius, we need to estimate the factor of safety against slip on the trial circle that's indicated in this figure. The trial circle is this line here, the rotational slip failure line. So, knowing that we have a radius of 16 meters and an angle of 72 degrees, we need to assume the pore pressures per unit length along the circle are given as 0.2 gamma h, where h is the mid-height of the corresponding slice. We also have some additional information in the table that shows us the heights of the slices, the angles that we would find usually from the tangential, normal and perpendicular to the tangential lines, the length of the base and the horizontal widths of the slices. The horizontal widths being this width here, here and here, as you can see on the diagram. So, as with any problem, first and foremost, we need to list the information that we have. So if we firstly take the information that we have, we know that phi dash is 28 degrees. We know C dash is 5 kPa. We know the unit weight is 19.2 kilonewtons per meters cubed. We know that our slip circle has a radius of 16 meters, r equals 16 meters, and the angle of that radius, which is theta, equals 72 degrees, which needs to be converted into radians. So, to convert degree into radians, we need to times by pi and divide by 180. Which equals 1.26 radians. So now, furthermore, we also know that U, as in the pore pressure per unit length along the length, is 0.2 gamma h. Okay, so we know that we're being asked to use the method of Fellenius, also known as the Swedish method of slices. So therefore, if we use the equation formula that we have here, the Swedish method of slices is this one at the top here. So F equals C dash R theta plus the sum of W cos alpha minus UL tan phi dash, give us our strength of the soil to resist the rotational failure, divided by the total force imposed by the weight of the soil, W sine alpha. The reason it is the sum of, because it is the sum of each slice of those elements. So therefore, the next step that we need to do is to put together the table for that equation. So looking at that equation, we need to know these elements. We need to know alpha, cos alpha, UL, what tan phi dash is, and sine alpha. So therefore, we can go back to our diagram here. We know we have 3 slices that we're looking at, and this is the information that we have about those 3 slices. So, if we transfer that information into a table, okay, so once we've put together the table like this, with the correct headings that align with the equation that we have, we can transfer the information from the table that we've been given to the table that we've produced. So the height of the slice is h. That's the height in the center midpoint of our slice. So that is 1.3 meters. 3 meters and 1.6 meters. The width of the slice is the horizontal width of the slice, also denoted as B. 3, 3 and 4. Now W equals H times B times the unit weight. That is because we are taking the area of the trapezium times by the unit weight of the soil to get the full weight force of the soil, W. Okay? So that is 3 times 1.3 times 19.2, which is 74.88. Then we have 3 times 19.2, which is 172.8. Then 1.6 times 4 times 19.2 was 122.88. Now we go back to the original table that we've been given to populate our alphas. So the alpha value there, as you can see, is 2 degrees, 32 degrees and 45 degrees. So we have 2 degrees, 32 degrees and 45 degrees. So from those values we can now calculate the cos alpha and the sin alpha. So cos of 2 equals 0.99. Cos 32, 0.84. Well, 848 will go 85, and cos 45 was 0.71. We go for the sin alpha at the same time. So sin alpha, sin 2 equals 0.035, so we'll go for 0.03. Sin 32, 0.53, and sin 45, which is 0.71. Now we have W calculated and we have cos alpha, so we're able to calculate W cos alpha. So 74.88 times 0.99, 74.13, 0.85 times the respective W of that slice, 172.8, gives us 46.9. Then we have 0.71 times 122.88, gives us 87.24. At the same time we can work out W sin alpha. So we have 74.88 times 0.03 equals 2.25. 0.53 times 172.8, 91.584. Simply multiplying this value W by this value for the respective slice. So the last one, 0.71 times 122.88 equals 87.24. Okay, now if we want to go back to the original table where we were given L, and L is the length of the base of the slice. That's this value here. So going back to the diagram, L is this length of the tangent from there to there. there to there at the angle, so there to there. That is L. So taking the values that we've been given in the table, we can transfer them into our new table, and we can take 3.01, 3.53 and 5.65. U is calculated, and if you remember, it was given to us that U equals 0.2 gamma H. So 0.2 gamma, so 0.2 times the unit weight, 19.2, gives us 3.84. So 0.2 times gamma equals 3.84. Therefore, U is 3.84 times the height of the slice in the midpoint. So 3.84 times 1.3 is 4.99. 3.84 times 3 is 11.52. 3.84 times 1.6 is 6.14. So now, to get the pull pressure, the full pull pressure, as in the total pull pressure along the length of the base of the slice, we need to times the unit length of pull pressure by the length. So that's 4.99 times by 3.01. That is the UL portion of our equation. So 3.01 times by 4.99 equals 15.02. 3.53 times 11.52, 40.67, and then 5.65 times 6.14 equals 34.69. So now we need to move to the next portion of our table. The reason that this has been written on another level is because I've run out of space in the page. As discussed in our lectures, you can often turn the page so that you're actually using it landscape if that makes it easier, but in the exam it is going to be portrait, so just be wary that you might need to put a next section of your table if you're doing this kind of equate the question. So if we go now, we need to cut the same corresponding slices. We want to do W cos alpha minus UL. So that is essentially what we have calculated for this slice for W cos alpha minus the UL which we have calculated. So 74.13 minus 15.02 for slice 1. $146.9 minus 40.67 for slice 2. This is us working out our effective stress. So that is the total stress due to the soil minus the pull pressure, UL being our pull pressure. And then finally 87.24 minus 34.69. 52.55. Now the next part of working out our shear strength of soil is to include the angle of coefficient of friction, which is phi dash. So tan phi dash gives us the next part of our equation. Remember, phi dash was 28 degrees. So if we work out tan of phi dash equals tan 28 degrees. So make sure your calculator is set to degrees when doing this calculation. Tan 28 equals 0.53. So therefore now we can multiply that portion of the equation by 0.53. So 59.1 times 0.53 gives us 31.33. 106.23 times 0.53 gives us 56. 0.30. 52.55 times 0.53 gives us 27.825. So now we can work out the sum of W cos alpha minus UL times tan phi dash, because that is the sum of everything in this column. So if we work out the sum of those, we have 27.825 plus 56.30 plus 31.33 equals 115.46. Okay, the next thing that we need to work out the sum of for our final equation is the sum of W sine alpha. So the double sum of W sine alpha, if you remember we worked out W sine alpha, that is the sum of this column of values. So 2.25 plus 91.584 plus 87.24 equals 181.07. Now, what we mustn't forget now, that's really important, is that we also need to include the apparent cohesion resistance along the slip plane. That is calculated by C dash times by the radius and theta in radians, which we worked out earlier. So to work out, we take C dash equals 5 kPa, which we were told from the question. So 5 times the radius of 16 meters times 1.26 radians equals the kPa resistance. So 5 times 16 times 1.26 equals 100.8. So F equals 100.8, which is C dash times the radius times by theta, plus the sum of the W cos alpha, so the effective stress, times by the angle tan to the angle coefficient of friction, which is the sum of this column here, 115.46, and then divided by the total force that's imposed due to the weight of the soil, which is the sum of W sine alpha, which is worked out here of 181.07. So 100.8 plus 115.46 divided by 181.07. This is greater than 1 and therefore could be considered safe. However, what you do want to be cautious of is that just because it's greater than 1, ideally you want a value between 1.2 and 1.4 to truly consider it a safe and stable slope. And that is how we calculate the stability of this slope shown previously using the Fellenius method as stated.